This is a whole picture of our proposed interactive classroom system. Now I'd like to expand it by going through all its modules. The first module would be the data input. In our app, after uploading data, user can choose any features to be included or excluded for the clustering. Once all features have been selected, the system will call recurrent neural network to develop representations for all patients or patient journeys. Those representations have incorporated both the temporal characteristics of the data and the relationships among individual medical events. After we achieved initial patient or patient journey representations, we can then run a general clustering algorithm, for example, k-means, to get an initial clustering result. Our clustering app is quite flexible. Currently, we provide 3 different clustering algorithms. They are k-means, hierarchical, and spectral clustering algorithms. The user can choose which clustering algorithm they want to use and how many clusters they want to have. The system also provides a function to recommend the best number of clusters that users should choose based on the nature of uploaded dataset. Then the system will do the visualization based on the clustering result. We currently provide 2 types of visualization in our system. They are scattering and hierarchical visualization. In the scattering visualization, each data point is a projection of each patient. Different colors stand for the different cluster labels, all the clustering results produced by the chosen clustering algorithm. And for the purpose of the demo, we specially add the shapes as a ground truth or the user's opinions. In the hierarchical visualization, we can see the result from a different angle, or consider a hierarchy of the clustering result. As we can see from the example here, in the top level, which is level 1, we have 3 clusters, and each level 1 cluster also has some subclusters. Based on the visualizations, the users or experts can investigate any data point and provide feedback in our system. For example, the expert can compare any 2 data points by clicking on the points directly. The user can also investigate an area of points. The system even provides a recommendation function to automatically choose the data points that most need to be investigated, such as the points near the edge of one cluster and also close to a second cluster. On top of this, the users can also utilize the powerful built-in functions for statistical analysis, such as to see the statistical analysis inside each cluster. After all the investigation and analysis and inputting the feedbacks, the user can call metric learning to consume the feedbacks by clicking Update Clustering. As introduced before, metric learning runs behind the scene to transform the original space into a new space, while similar objects stay closer and different objects stay further away. And if we run the general clustering again in the new space, we should be able to achieve a more fit-for-purpose clustering outcome. If the users are still not satisfied with the outcome, they can review the result and do labeling again, and call metric learning again to continue improving the clustering performance. This process will be repeated until the clustering result satisfies the expert. Well, in our example, after several iterations of metric learning, the final clustering outcome is like this. Compared with the initial clustering result, firstly, the current clustering result represented by the colors totally matches the ground truth represented by the shapes. Secondly, in the new space, the similar patients do get closer, while the different patients do get further away. So, I would say, with the interactive metric learning's help, the clustering now becomes fit for purpose. Generally speaking, there are many benefits to a robust and fit for purpose patient journey clustering. For example, we can work out what happens to the most common or typical patients. We can also compare what the best practice guidelines say should happen to a patient group to what actually did happen to that group. Finally, we can look at patients who appear to have received too little or too much health services when compared to what most people receive. Finally, I would like to take a real-world healthcare application as an example. Our proposed framework is expected to contribute to a real-world project called Healthy Mind, Healthy Body. In short, studies in Australia and other developed nations show that life expectancy is shortened by up to 30% for clients of public mental health services compared to the general population. Mental health is a key priority for Australian governments. Improving the physical health of people living with mental health conditions is one of 8 priority areas for action, agreed by all Australian governments. The Healthy Mind, Healthy Body project aims to identify opportunities to prevent the cascading physical health and social impacts of poor mental health. More specifically, the Commonwealth Department of Health is planning to use this system to better identify patient groups with mental health conditions who may differ in their physical health. By comparing the clustering result of patients with certain physical illness and patients not only having the same physical illness but also having severe mental illness, the health experts will be able to better identify potential associations between mental and physical health conditions. This knowledge could inform policies that are designed to close the gap in life expectancy for those people living with severe mental illness.